Today, I'll be talking about aerial LiDAR measurements of oil and gas production infrastructure in the Permian Basin and what that can tell us about methane emissions and their distribution in that region. Let's see. Before I get started, I'd like to mention that this talk is currently undergoing peer review. It's in its second round. It's available on Earth Archive at the link that Evan sent out before the talk. Also, this one sent here points to the same place. The LiDAR measurement data that I'll be talking about hasn't been reported previously. This is sort of the first appearance of this data set. And I'd like to acknowledge my co-authors. Mike Thorpe, our CTO, may or may not be here in the audience. I haven't checked yet, but he'll be available for to help answer questions at the end of the talk as well. From very high level, what's going on in this research that I'll be talking about is that Bridger performed aerial gas mapping LiDAR surveys of oil and gas production surveys in the Permian. And we will align those data with campaigns conducted by Carbon Mapper using high altitude infrared spectrometry. So using both of these data sets allows us to perform a joint analysis and extend and reinterpret the methane emission distribution for the surveyed region. Just as a sneak preview of the results, the sort of main things that I'll be arguing here with these results are that GML is measuring emission sources that were missed by Carbon Mapper, and that these sources account for, in fact, most of the total emission rate in the region. Now, just to kind of jump ahead and see what this looks like on the plots, we can plot the detection density, which can be viewed as basically the frequency of these emitters as perceived by the sensors. So we can see the GML and Carbon Mapper distributions plotted here, and you'll notice that the Carbon Mapper distribution tends to roll off as we get to emission rates of hundreds and even smaller kilograms per hour, whereas GML keeps going to at least 10 kilograms per hour. That roll off indicates that in that survey, emission rates smaller than these few hundreds of kilograms per hour were detected at reduced probability. And a consequence of that is can be shown here. For example, looking at emission rates at 100 kilograms per hour shows that for every emitter detected by Carbon Mapper, there were actually 13 more out in the field that were detected by GML. Now, as a consequence of that, it means that these sort of mid-range emitters are contributing lots of methane that was previously undetected in this campaign. So if we look at the cumulative emission rate distribution, then we can sort of assess the significance and sort of the total emission rate that were contributed by those sources. So ignoring all of the other stuff on the plot, I would just point to the point distributions, blue and red. They're showing the GML and Carbon Mapper distributions. If we read the very top of those curves, what we've done here is just added up every emission rate times its persistence, or rather its density as observed in the field, and summed them all up from largest to smallest. What we're seeing here then at the top of the curves is the total cumulative emission rate detected by both of those campaigns. We see that GML is detecting more than twice as much as Carbon Mapper. The talk is organized as follows. We go through some background on catching methane emissions and how to go about doing that. Then we describe both technologies and the steps that we go through to align the two data sets. And finally, we dive into more details of the results that I was just showing on the previous slide. So methane emissions are sort of notoriously difficult to track and quantify and measure. If we had to boil it down, we would say it's because they are, number one, widespread. They're coming from many facilities, many pieces of equipment spread over a large geographic area. They're intermittent. So if you detect an emission one day and come back, it may not be emitting the next day, or even hour to hour or minute to minute. They're variable in size, going from emission rates around 1 kilogram per hour and lower to over 10,000 for the very largest events. So in response to these properties, measurement solutions need to achieve high scale and representativeness in order to sufficiently sample the population that you're interested in, and need to have high enough sensitivity to avoid missing the small but very common emissions that are out there. As I'll be describing in the next slides here, there are a couple of ways to achieve scale, and one is spatially by area coverage. This is basically just the number of facilities that you measure and that you intend to scan in the campaign. And the next is the number of times that you scan it. So this is a temporal coverage. The more times you scan a facility, the more likely you are to pick up on an emission that is going off intermittently. So I'd like to compare the two campaigns according to these properties that I was just discussing. Coverage, scan, sensitivity. We'll be filling in this table. And you'll notice that I've divided out Carbon Mapper into two date radios. This is because they performed two campaigns, one of them larger in 2019, and a second sort of smaller set of campaigns in 2020 to 2021. In terms of coverage, the Carbon Mapper campaign was a blanket or wall-to-wall study over a 55,000 square kilometer area that's indicated by these polygons on the map. In 2020 to 2021, they surveyed a smaller area that partially overlapped with these ones. GML, on the other hand, well, the GML data set that I'll be describing here is comprised of survey data from contracted client facilities within a 38,000 square kilometer subregion. And these surveys that we're all compiling together are comprised of infrastructure or facilities operated by 28 client operators. So we believe that this is representative of the mix in the larger region. In terms of number of scans, Carbon Mapper structured their survey to be able to measure the intermittency of the methane sources. So we can look at just generally the median number of scans in each study. For their 2019, it was the median number of scans was 6. In 2020 to 2021, they performed 4. And for GML, the surveys were conducted in more or less a snapshot fashion, where one flight was performed over all facilities that we intended to scan, and then reflights were called on facilities where an emission was detected on the first one. So effectively, what we have found, what we are reporting here is emissions that were discovered on one overflight. So because of these differences, Carbon Mapper did an excellent job of covering a whole entire area, of doing a large number of scans. They achieved a much larger scale than GML for the data in this region. So if you sort of control for those two factors, you would say that the Carbon Mapper 2019 campaign was 22 times larger. That's not to say that the GML's data set is small. In fact, it covers 7,400 facilities. And we'll show sort of closer to the end of the talk that this was enough to quantify the cumulative emissions to a reasonable range, about plus minus 10%. In terms of sensitivity, what we can do is compare the 50% detection probability for 2-meter diameter aggregated sources, and we'll talk about what that aggregation means. But basically, we're talking about pieces of equipment that are emitting, or point sources with a 2-meter buffer. For Carbon Mapper, the sensitivity appears to be around 300 kilograms per hour as a result of this study. And for GML, that sensitivity level is below 2 kilograms per hour. What this is saying is that Carbon Mapper is detecting sources at 300 kilograms per hour and below at significantly reduced probability. So they're going to be underrepresented in that part of their distribution. Whereas for GML, that threshold is below 2. As a consequence of this difference in sensitivity, GML saw detections at 38% of the scanned facilities, whereas Carbon Mapper was seeing emissions from 1.5% of the scan facilities. So what we'd like to do here in our analysis is utilize the advantages of each data set, right? So Carbon Mapper achieved really impressive levels of scale with a huge blanketed survey and a large number of scans for every facility. Whereas for GML, the value added is a sensitivity, and as we'll describe in some of the next slides, spatial source resolution going very fine down to about 2 meters. So although these are two aerial campaigns, aerial is by no means the only game in town. So I'd like to just mention that there are other technologies out there. If we sort of organize them in terms of number of facilities that can be measured per sensor head, it would look something like this. So at the top, we have satellites, which maybe don't have the best localization, but are able to measure over very large geographic regions. And then optical gas imaging and fixed sensors at the bottom, which are typically one per site or maybe a few per site. Then in the middle are these aerial campaigns and mobile sensors, which two of which I'll be reporting on today. All right, so that is about methane and sort of the approach that we're taking with these two data sets. In this part, I'd like to describe the two technologies and then the steps that we go through to align the Carbon Mapper and GML data sets. Carbon Mapper's platform is an airborne hyperspectral imaging camera. Now, everyone is familiar with a regular camera that records images as a function of two position coordinates, X and Y. This type of hyperspectral imaging camera is a push broom, which means that it records images in X and wavelength. And then that is translated over the flight path of the plane in order to yield, after that whole scan, a 3D image where you have two position variables, X and Y, and also wavelength. The system detects gas plumes, in particular methane absorption features around 2300 nanometers. And the illumination source is backscattered sunlight from the ground. In this campaign, the flight altitudes used were relatively high at 4.5 and 8 kilometers, which is something important to keep in mind here. By comparison, the gas mapping LiDAR platform is a georegistered area laser spectroscopy probe that's flown at a much lower altitude, about 200 meters. And this laser probe is basically a wavelength scan system that's focused on the narrowband of absorption feature of methane around 1651 nanometers. This type of active illumination wavelength modulation spectroscopy system is insensitive to environmental parameters such as terrain reflectivity and solar angle. That is relatively speaking. Now, what this does is measures gas concentration as a function of position, and coupled with every detection is information like plume height and wind speed, which is used to calculate the gas flux. Now, as I mentioned, the flight altitude for GML was 200 meters, whereas for Carbon Mapper, the flight altitude was 4.5 and 8 kilometers in the campaigns that we're talking about here. So perhaps as a consequence of this altitude difference, the source resolution is vastly different. So consider this site, for example, that was flown by both campaigns. On the left, the Carbon Mapper plume image is showing maybe one, maybe two emitters on this site that are not really well resolved. It was a little bit of an unfair comparison. The wind speed here was probably pretty low, just judging by the looks of it. But you can see that on the GML plume imagery, we're able to distinguish many different plumes. And each one of these sources is resolved to about 2 meters. For example, looking at that tank battery, we can see that each one of these tanks is actually emitting. And that 2 meter buffer is shown by the red shaded circle around each dot. Now, this is pretty significant. The source resolution is pretty significant in terms of comparing distributions, because plumes in an aggregation area, Carbon Mapper used an aggregation area of 150 meters, are going to sum up, and those are going to give us larger emission rates than if we had looked at those individual plumes, like as shown in the GML picture. So this is something that we're going to have to consider, and we'll be really clear about which aggregation we're using in the results. Another thing that we need to align is how to treat the number of overflights. As I mentioned, GML was essentially a single scan, whereas Carbon Mapper was highly, highly multi-flight. So just to give a feel of what the significance is here, say that you have say that you have an emitter that emits half the time, and you fly over it twice. Then you have a 75% chance of picking up a detection from that emitter, as compared to if you fly it once, you have just a 50% chance of picking up that emission. So we see this, borne out over many more flights for Carbon Mapper, which means they picked up many more emissions per on a given facility than GML would have. Now, the way that we control for this is to convert to what we call a single scan equivalent, where we plot all of the emission rates in terms of their emission rate when they were detected. So from a multi-flight campaign like Carbon Mapper, you might get a persistence adjusted value, which is the time averaged rate. This is the average emission. This is the sum of the emission rates over the number of times you flew that site. So starting from the blue point on the density curve, or the detection frequency curve shown at the bottom, you can then divide that by the persistence in order to get the average rate when detected. Okay. Now that we've done that, we need to make sure to adjust the density by the frequency. If you had just gone out one time to scan that, you're going to detect that with a probability of the observed persistence. So the transition, sort of the mapping from this persistence adjusted distribution, which is often how these things are plotted, to a single scan looks something like this on density versus emission rate. This mapping is going to affect all of the ways that we plot it. For example, if we plot the cumulative emission rate as shown on the right, what this looks like. By the way, again, the cumulative emission rate is just the sum going from largest to smallest of all the emission rates times their density or persistence in the field. So what we get using this mapping is mostly a shift from those time average rates to the average rate when emitting. So this curve shifts over, and there's a slight reshaping of the curve as these points change order in the distribution. So for all of the analysis that we'll be showing in the results, we're going to be using a single scan equivalent, which is accessible to both campaigns. Okay, so just to summarize what we need to think about for the data alignment. First of all, sensitivity depends on not only the technology, but a lot of different flight parameters, which are unique to each campaign. Maybe most important of which is the altitude, but there are lots and lots of others. Source emission rates that we plot and that we're going to be comparing these distributions on depend on both the spatial aggregation, in which we'll be looking at two different forms, one at 150 meters, another at 2 meters. And secondly, the number of times that each site is flown. And for this, we'll be using the single scan equivalent. Next, I'd like to dive in deeper to the results. And before we do that, let me just explain that the results shown here apply to the particular campaigns under study, meaning using those flight parameters that are so important in determining the results at the specified source resolution, meaning the aggregation level that we'll be talking about. For example, if Carbon Mapper had flown, say, at a lower altitude, their sensitivity maybe would have been better, and so they would have picked up more sources that are smaller. But in this case, what we're looking at is the realized detection sensitivity for that campaign. So that's the sort of significance of the sensitivity values that we'll be reporting. Okay, so we've gone through all of this effort to think about how to align these two data sets. And we think we've done a good job of it, but what we'd really like to do is do some sort of statistical test to make sure that we're not making any mistakes. So the way we'll go about this is to compare the GML and carbon mapper distributions where both of them measure the true frequency of emissions. Now we need to make sure that we choose an emission rate that's large enough that the probability of detection was not degraded in either study. We choose, so that sort of threshold, which we can set more or less arbitrarily as an input to the analysis, is called the full detection limit. So at rates above the full detection limit, we're saying that the probability of detection is 1, and below that, it starts to degrade at some point. So we've set that at 600 kilograms per hour for carbon mapper, and for GML, it's much lower, as we'll see in some of the later plots. But in this one, you can see that the survival function, it starts at 10 to the 2.8, which is 600. Okay, so the statistical test we'll be doing here is on the Kolmogorov-Smirnov statistic, which is just the maximum difference between the two CDFs or survival functions, and that's shown by the black vertical bar in the plot down there. If the p-value associated with that is really small, less than say 5%, then we would say that there is a statistically significant difference between the distributions. Now in this case, the p-value was much higher than that, so we would say that there is no evidence to suggest that these are in fact different, and we are free to assume that these in fact are the same distribution. Having done that test and all of the alignment steps, we then proceed with the joint analysis. What we'll do here is fit a model function to both data ranges above each's full detection limit, which for 150 meter sources, as I mentioned, is 10 kilograms per hour for GML. The model agreement is quite good, except at emission rates are around 3.5, 10 to 3.5 kilograms per hour, as indicated by that arrow. That has some implications that we'll mention in later slides. And to get these fits, we used maximum likelihood, which fits the data on density function, which fits the data to the density function curve, and information analysis to select the best model function from a set of candidates. In this case, it's log normal for the 150 meter sources. It's actually a little different for the 2 meter sources. And finally, the likelihood ratio method to find the model's 95% confidence interval. Okay, so having done that analysis, we're now free to dive into some more detailed results on these two plots that I was showing at the beginning of the talk. So first, we'll go into the detection density. So from the density plot, we see indeed that the density increases with smaller and smaller emission rate until at least 10 kilograms per hour, as revealed by GML. And the shape of this distribution is not linear. The fit here, as I mentioned, is a log normal, and the sort of roll off, the sort of flattening of this curve does not indicate reduced probability of detection for GML. Instead, rather, that's just the shape of the distribution. Next, we can then find the carbon mapper detection sensitivity to sort of give an idea of whether we chose the right full detection limit and sort of threshold below which we can expect that emissions are underrepresented. And we do that by comparing the model to the measured distribution from carbon mapper, and doing that, as shown in the inset, shows that the 50% probability threshold is at 280 kilograms per hour. Right, so this result was for 150 meter sources. Now we also want to consider a 2 meter source resolution. And to do this, we use a similar joint analysis where we compare GML and carbon mapper above the full detection limit. And what we've done is filtered the carbon mapper data to single emitter detections based on plume imagery. So their data set comes with plume imagery that is, for some sites, is rather complicated, and you can see multiple point emitters, and in some cases it's really questionable. And sometimes you just see one point emitter on a site, and it's pretty obvious just from the way that the plume is shaped that there's one emitter on the site. So we've taken that set of emissions or that set of images to create their distribution for 2-meter source resolution. And doing this, you can compare the 150-meter source aggregated distribution to 2-meter sources, for instance, for GML. And of course, as you'd expect, there are more equipment level sources than there are facility or 150-meter sources. And you can see that by, for instance, looking at 10 kilograms per hour on this plot and see, oh yeah, they're 8 times more. What you also might notice is that this curve is a little bit straighter than the 150-meter aggregated curve. So this is sub-log normal. This is not quite like a power function, but it's not a log normal. It's actually somewhere in the middle. So yeah, I guess the takeaway from that is that the spatial aggregation is causing that distribution to flatten out a little bit more as the emission rates decrease. We can then rerun that same sensitivity analysis to find roughly the same value, around 300 kilograms per hour for carbon mapper. Okay, so those are some of the takeaways from the density plot. Now I'd like to move on to the cumulative emission rate plot that I was showing you at the beginning of the talk, and we can get a lot more information out of it now. First thing you'll notice is looking at the carbon mapper distribution of the dark red points on the plot, is that that curve actually lies outside the expected sample error range. Now that sample error range shows the 2.5 and 97.5 percentiles of a Monte Carlo simulation, assuming a sample of equivalent size. So this, if the model is right, that should be a pretty good estimate of what we expect that variation to be. Now, carbon mapper comes outside of that point at around 10 to the 3.5 kilograms per hour, which is where we noticed that sort of deviation outside the model before on the previous slide. Now, what that means is perhaps, there are actually a lot of things that could be causing that, but perhaps the distribution is not actually log normal in the very tail end of the distribution, even though it does seem to fit that description throughout the rest of the curve. In any case, more measurements of the very end of the heavy tail should bear that out. Now, what I'd like to do here is read off some of the total values in order to compare how these two campaigns did and what that means about the total emissions that are out there. So we'll be reading cumulative emissions at this 10 kilograms per hour threshold, which is indicated on the plot. And we'll be reading those values as shown by the horizontal lines here. The reason we read at 10 kilograms per hour is because that's the full detection limit of GML. And so that's the range through which the model should be valid. There are emitters below 10 kilograms per hour, of course, but because we're not doing any probability compensation, we're not considering that for the totals. So any of the totals that I say here are the true total is actually larger. Right. So for sources greater than 10 kilograms per hour, GML measured 91% of the cumulative emissions predicted by the model, whereas carbon mapper measured around 40%. And the results for the 2020 to 2021 campaign were similar. Now, these numbers are pretty significant in terms of what the total emissions from the region are. Carbon mapper's authors reported that their measurements represent 59% of the total methane, regional methane flux as determined from satellite measurements. In fact, comparing to GML, that number appears to be lower at about 40%. So this is saying that methane emissions from the surveyed area are in fact higher than previously reported and understood. And as I mentioned, we're ignoring emission rates below 10 kilograms per hour. So in fact, there are even more emissions than we are saying in this 40% number. Right. So all of that was for 150 meter sources. And now we'd like to relax that spatial aggregation and just look at the distribution for 2 meter sources. As you'd expect, because emission rates are smaller, the sort of center of mass of this distribution shifts to smaller rates. And you can see that by comparing the 2 model functions for facility sources and equipment sources shown in the plot. As I mentioned, the GML sample consists of surveys over 7,400 sites. And you can see that allows us to quantify the cumulative emissions pretty well to within about plus minus 10%. You can see that by comparing the sample error range to what was actually measured or the model function. Now, another insight that we can gain from curves like this is the sensitivity required to detect a certain portion of emissions. For example, if we're interested in detecting half of all emissions from 2 meter sources, we look at 0.5 on the cumulative emissions on the plot and then read off that value. And that value comes out to be 46% on the, 46 kilograms per hour on the x-axis. This is assuming that the sensitivity cuts off like a step function there. So this 46 gives a sort of rule of thumb estimate of what the sensitivity needs to be in order to detect that portion of emissions. And it's the true sensitivity is actually a bit lower than that for a couple of reasons. Again, because we're ignoring sources smaller than GML's full detection limit, which in this case is 3 kilograms per hour. And also for other basins, this tends to be smaller to begin with, just because Permian emissions tend to be larger. Finally, that brings us to the end. So the story here is that we aligned Carbon Mapper and GML datasets and tested that alignment using the Komarov-Smirnov statistic. We performed a joint fit that's informed by sort of the best qualities of both datasets, Carbon Mapper scale and GML's sensitivity and source resolution. Then in the results, we showed some memorable numbers, and I'll kind of leave on that note. First of all, Carbon Mapper's 50% detection sensitivity was around 300 kilograms per hour for both 150 meter sources and 2 meter sources. GML's distribution indicated that there is at least 2.3 times greater total emission rate for 150 meter sources, and that at least half of the total emission rate for 2 meter sources comes from sources with rates below 46 kilograms per hour. With that, I'd like to thank you for your attention, and I'll take your questions.